What if I told you that 0.99999 repeating forever is actually equal to 1? Sounds crazy, right? It feels like it should be just a tiny bit smaller than 1. But what if I told you that there is no number between them? And we're going to go ahead and prove just that using infinite series, limits, and some algebra. So the first thing we're going to go ahead and do is a simple algebra trick. Let's start by defining x to be equal to 0.999 repeating, where the little dots that are drawn right here are simply repeating decimals. Then the next step is going to be to multiply both sides by 10. X times 10 is 10x. 0.999 times 10 simply shifts all the digits one place to the left. Now, what we're going to go ahead and do is subtract x from both sides. So 10x minus x is going to be 9x. 9.999 repeating minus 0.999, that's simply going to be 9. Now the next step is to divide both sides by 9, and we obtain that x is equal to 1. Therefore, we have proved this. Now let's go ahead and do something just a tad more rigorous than the algebraic proof that we have just done. Now let's go ahead and break down 0.999 repeating down into an infinite sum. So 0.9 plus 0.09 plus 0.009 plus 0.0009, and it's going to go on and on and on. Now for an infinite geometric series, we use the formula s sub infinity equals a over 1 minus r, such that the absolute value of r is less than 1. In our case, r is equal to 0.19 and a, the first term, is equal to 0.9. Now let's go ahead and substitute the values into the infinite geometric series formula, and we obtain 0.9 divided by 1 minus 0.1, which is 0.9 divided by 0.9, which that is simply going to give us an answer of 1. So once again, we proved this. Now let's use limits to prove once again that 0.999 repeating is equal to 1. Let's think about 0.999 repeating as a sequence of numbers getting closer and closer to 1. Each term in this sequence has more 9s, therefore getting closer and closer to 1. How close does it get? Let's use limits to find this out. We can define a sub n as equal to 1 minus 10 to the negative n, such that n is the number of decimal places. For example, when we use the term n is equal to 1, we get 1 minus 0.1, which is equal to 0.9. When we get n is equal to 2, we're going to go ahead and get 1 minus 0.01, which is equal to 0.99, and so on. Now let's find the limit of this sequence as n approaches infinity. So that limit is going to equal the limit as n approaches infinity of 1 minus 10 to the negative n. Now we know that as n goes to infinity, 10 to the negative n is going to shrink towards 0. That means our sequence gets closer and closer to our limits, which is equal to 1. And so once again, we have proved this. Now, I know that some people still aren't convinced. Maybe this feels like a trick or a technicality. So let's talk about what it means for two numbers to be equal. If 0.999 repeating and 1 are different numbers, there should be a number between them. But there isn't one. That's because the difference between those are exactly 0. In rigorous math, equality means that there's no difference, not even an infinitely small one, and that is why we can say with full certainty that 0.999 repeating is equal to 1.